Every minute, the world's AI clusters consume enough power to run a small city. On Earth, we are hitting a wall, grid connection lead times of 7 years, skyrocketing cooling costs, and a looming 945 terawatt-hour electricity cliff. But what if the solution to our planetary energy crisis isn't on the planet? For decades, the $10,000 per kilogram launch cost was the ceiling of human ambition. Today, that ceiling has collapsed. We are approaching a $200 per kilogram inflection point, where the physics of the stars beat the economics of the ground. This is the birth of unfettered compute, a new asset class where AI training is decoupled from national grids and relocated to a 365-day solar window. But for the VC, the policy advisor, and the sustainability consultant, this migration is not a frictionless vacuum. It carries the weight of orbital e-waste, thermal physics, and a jurisdictional mirage.
The logic is driven by two variables: energy and land. In major markets, data center expansion is stalled by decaying infrastructure. In contrast, a heavy-lift launch can deploy a megawatt of capacity in weeks. Google's Suncatcher analysis identifies the $200 mark as the moment sun-synchronous orbit provides energy density Earth can no longer match. While terrestrial racks struggle to cool 60-kilowatt loads, space offers a limitless sink if you can master the engineering. The StarCloud-1 mission proved the physics, training a Shakespearean language model on a single orbital GPU. By late 2026, StarCloud-2 aims to scale this by 100x. For infrastructure funds, the launch cost curve is now the only chart that matters. If launch costs hit sub-$100, the terrestrial data center model is effectively disrupted. However, space is not a sanctuary. It is a brutal laboratory. Beyond the roadmaps of firms like Lumen Orbit lie the laws of thermodynamics. In a vacuum, you lose the luxury of air. Every watt of heat must be bled out through massive radiant wings. If these radiators become too heavy, they negate the very launch savings investors crave. Then there is the radiation risk. Standard silicon is fragile. Cosmic rays don't just cause glitches, they cause hardware decay. While shielding helps, it adds mass and unit cost. Finally, we face a jurisdictional mirage. The 1967 Space Treaty offers no guidance on data residency. For policy advisors, the Q3 2026 FCC decisions on spectrum will be the material gate that determines if these assets are even legal. We must also address the environmental debt. To be truly green, rockets must be 10 times cleaner than today's fleet. From a resource management perspective, we are currently facing a circular economy failure. AI hardware has a lifespan of 3 to 5 years. In our current model, we are launching strategic minerals into a single-use orbital grave. Every deorbited satellite is a lost resource, burnt to ash rather than returned to the industrial loop. Without standardized life cycle cost accounting and orbital recycling, space-based AI risks becoming the ultimate planetary scale externality. The path forward isn't a total migration, but a hybrid infrastructure. While orbit is ideal for asynchronous AI training, real-time inference still requires a terrestrial heartbeat due to latency. The winners in this sector will lead with 3 pillars: modular architecture, allowing incremental capital deployment to hedge against technical failure; in situ recovery, establishing de-orbit standards to reclaim rare earth minerals;
and solar space hedges using high capacity factors to protect against volatile Earth-side energy prices. By 2030, we will know if orbital compute is a structural solution or merely a new way to export our waste. The infrastructure of the 21st century is leaving the atmosphere. Are you prepared for the crossover? Subscribe to Conscious Terror for curated signal on the energy transition, from the grid to the stars. Let's build an economy that doesn't just scale, but sustains.